So there's a children's book called Knuffle Bunny, a cautionary tale. This is also a cautionary tale, albeit a somewhat more boring one than Knuffle Bunny. But I'm going to drag you through it anyhow because you should see an example of how rounding error analysis is worked through in detail at least once in the course of this course. So remember our basic model of floating point arithmetic, which is that if you want to know what the value of a plus b in floating point is, you take the true value and it's good to within some small relative error, where that relative error is bounded by machine epsilon, about 10 to the negative 16th for double precision numbers, assuming that you don't overflow or underflow or do something exceptional. So each operation generates a small relative error, which means that when you do a sequence of operations, you have to figure out how each operation's contribution to the error is going to propagate through the rest of the calculation. So let's consider the MATLAB calculation y equals 1 minus square root of 1 minus z. This is the smaller root of a quadratic. Really, that's several basic operations. You first compute 1 minus z, then you compute the square root of 1 minus z, and then you compute 1 minus the square root of 1 minus z. So at each step, you contribute a little bit of rounding error to the ongoing calculation, and each contribution is on the order of machine epsilon. So let's chase those contributions through and see how they add to the final rounding error. So in the first step, you compute the floating point value of 1 minus z. So that's 1 minus z times 1 plus some delta 1. And now we're going to compute the floating point value of the square root of that computed 1 minus z. So that's going to be the square root of the computed 1 minus z times 1 plus some delta 2. Right? So now we really want things in terms of the true value. So we're going to write t2 hat, our floating point number, as t2, which is the square root of 1 minus z, times the square root of 1 plus delta 1. That's how the first rounding error has propagated through in this calculation, times 1 plus delta 2. Okay, so that's just algebra on our formulas for t1 hat and t2 hat. Now, the expression square root of 1 plus delta 1 times 1 plus delta 2 is pretty awkward. We'd like to approximate it. And what we're going to do is to Taylor expand that whole thing about 1. So this is looking at the Taylor expansion for delta 1 and delta 2 very small of square root of 1 plus delta 1 and of 1 plus delta 2. And what that's going to give us is about 1 plus a half delta 1 plus delta 2. If that seems completely mysterious, you should go back and check your calculus, but that is what it is. So that means that our relative error here is going to be some delta 2 hat, which is a half delta 1 plus delta 2, roughly speaking. And so the size of delta 2 hat is bounded by a half the size of delta 1 plus the size of delta 2, or about 1.5 times machine epsilon. So this is still on the order of 10 to the negative 16th. Okay, that's the first step. So now let's see how the error propagates through in the next step. So t2 hat is the true value t2 times 1 plus delta 2 hat, which is about 1.5 machine epsilon. And t3 hat is going to be the floating point value of 1 minus t2 hat. So that's 1 minus t2 hat times some additional relative error term, so 1 plus delta 3. Okay? Now we want to again get t3 hat in terms of the true t3, right? So the true t3 is 1 minus the square root of 1 minus z. So what this means is we're going to take the error that was propagated through to get t2 hat, and that's going to be an absolute error of t2 times delta 2 hat. Right? Well, that's an absolute error. That's not quite what we want. So we've now got an expression that involves 1 minus t2. That's good. But then that's minus t2 times delta 2 hat, not times 1 plus something, right? So it's relatively easy to get it in terms of relative error. What we're going to do is pull a factor of 1 minus t2 out from that expression, right? So now we've got t3 hat equals 1 minus t2, which is the thing that we really wanted, times 1 minus t2 over 1 minus t2 times delta 2 hat times 1 plus delta 3. And again, doing our first order error expansion trick, Taylor series in another name, we're going to write this as t3 hat equals the true t3 times 1 plus delta 3 hat, where delta 3 hat is now going to be minus t2 over 1 minus t2 times delta 2 hat plus delta 3. Now the problem is that 1 minus t2 could be pretty close to 0 if t2 is pretty close to 1. So that's going to look like something that's close to 1 over 0 times delta 2 hat plus delta 3. So we've taken our little error from the contribution of square root of 1 minus z and suddenly amplified it enormously in a relative sense. And this is cancellation. Okay, so this is a general problem. If you take two numbers that are very close together, much closer than the larger of the two, so that the difference is really small, then a small relative error in either of the inputs may be big relative to the difference. Okay, so that's a problem, but it's a problem that we can get around. So for this particular example, how would we rewrite things in order to avoid the cancellation? Well, there's a standard trick, which is when you've got something unpleasant, multiply it by 1. So in our case, we're going to take 1 minus square root of 1 minus c and multiply it by 1 plus square root of 1 minus c over 1 plus the square root of 1 minus c. Right? So now you do a little bit of algebra, and you get that this is equal to z over 1 plus the square root of 1 minus c. Right? So if we wrote a MATLAB code to evaluate that thing and broke it into steps as we did before, then the first couple of steps would be the same. The third step, we would change a plus to a minus, or rather a minus to a plus, and then we have an additional division. Okay, so how does that fix things? Well, the first two steps of the error analysis are the same as before. The third step, we're just changing a plus to a minus, or a minus to a plus, right? So we've now got, again, something that's going to be our computed value is equal to the true value plus times 1 plus delta 3 prime, right, where delta 3 prime is the analog of the delta 3 we had before. But now delta 3 prime, rather than involving this ratio of t2 and 1 minus t2, is going to involve the ratio of t2 and 1 plus t2, right, which is less than 1, always less than 1, right? So that means that the size of delta 3 prime hat is no bigger than the size of delta 2 plus the size of delta 3, right? So this is going to give us, I've written 1.5 machine epsilon, but really 2.5 machine epsilon of error. Okay, so now does the division hurt us? Remember that multiplication and division can't actually amplify relative error. That's something that we briefly alluded to in the first video. So that means that our s hat 4, I screwed up a subscript, but that's okay, is going to be the true value of s4 times 1 plus delta 4, so that's the piece of the error that we picked up from doing the floating point division, divided by 1 plus delta hat 3 prime, so that's the error that was inherited from the computation of s3, right? So we're going to again write that as 1 plus delta 4 hat, where delta 4 hat now is roughly delta 4 minus delta 3 prime, right? So that means that the size of delta 4 hat is going to be bounded by the size of delta 4 plus the size of delta 3 prime hat, so about 3.5 machine epsilon.